Now that we're really well acquainted with linear equations, slope-intercept form, finding slope-intercept form from a point and a slope or just 2 points, now that we've got that figured out, we're now ready to write linear equations from graphs and from context. Now, when we say context, what we mean is inside of a situation, inside of a story problem. So they're going to give us a bunch of information and we need to interpret that and figure out what linear equation would represent that situation. So let's take a look at the warm-up. Just a quick reminder here. If you think I'm beating this to death, I am, because these are formulas that people forget all the time. So remember, if we've got a graph, then we think of slope as the rise over the run. And if we've got 2 points, then we think of y2 minus y1 over x2 minus x1. Slope-intercept form, again, we've got to make sure we have that memorized. Y equals mx plus b. Gosh, if you don't have that memorized at this point, we've said it probably 100 times in class so far, so make sure you've got that memorized. Another name for slope, we haven't talked about this in a while. We talked about this a whole bunch in the last unit. Another name for slope is the rate, okay, or also the rate of change. How much are the points changing, both the x and y coordinate, from one measurement or from one point to the next point? So rate or rate of change. When anybody says rate, you should automatically think slope. And then what is the x coordinate of every y-intercept? So remember, stop and think about this. If it's on the y-axis, if it's a point on the y-axis, what that means is we didn't go right or left. That means the x coordinate has to be 0. So the x coordinate has to be 0 to be on the y-axis. That's why sometimes we would write it down as 0 comma b. We mentioned that especially in one of the examples a while back. So let's run through the ideas of this section. Linear equations can often be used to represent real-world situations. All right, that's when they become really useful. We're going to look at some linear equations that are used in the context of real-world problems. And in order to do this, we're going to make a couple of adjustments to the vocabulary and the way we've been talking about slope-intercept form and different things like that. So we're going to think of the y-intercept as the starting point. Okay, starting point, or the starting value. We talked about it being anchored at that point, and then we use the slope to get to other points. We're going to call that the starting point, or the initial value. And we're going to refer to the slope as the rate of change. So we use those interchangeably. If somebody's talking about rate, they're talking about slope. If they're talking about slope, they're talking about rate. So it says write an equation for each graph by identifying the starting point and the rate of change. Now when we say starting point is going to be 0 comma whatever. So think back when we'd use tables, a lot of times we said, hey, it's good to have 0 and then a couple negatives and a couple positives. Well, we're going to think of 0 as that starting point right here. So let's find where the y-intercept is. Let's find our starting point. So if x is 0, we might have to go up to find the line. We might have to go down to find the line. On this particular one, we go down. So the starting point is 0, -4. So it starts at a value of -4. The y value of -4, and then we need the rate of change. We need the slope. So on this one, we're going to go down 1 and right 1. So -1 for the rise, 1 for the run, or we could do, say, from this point to this point, down 3 and over 3. Either way, when we find that, it's going to be -1 on the top, 1 on the bottom, so it's going to be a rate of change of -1. So I'm going to put a dotted circle around the two of those. Those are parts of the answer, but here's the equation that we're after. We're after y equals whatever the rate of change is, -1 for the slope, and then whatever the y-intercept is, whatever the starting point is, so that would be -4. Okay? Now you'll notice that I put a -1 here. If I don't want to put the 1, I don't have to, but it certainly doesn't do any harm, but that would probably be the best way to write the answer, with just the negative in front there, and we assume that it's a 1. Okay, let's take a look at the next one. We need the starting point, so again, it's going to be wherever we are on the y-axis. Okay, so the starting point is going to be 0 comma, in this particular case it's also 0. Now we need the rate of change. Let's find some convenient points. Probably this one right here, rise 2 and run 3. So if we rise 2 and run 3, that would be a slope of rise on the top, run on the bottom. So there we go. And then the equation would be y equals the rate of change, 2/3 times x, and then plus whatever the y-intercept is, plus 0. I'll put a circle around that. Again, we probably wouldn't put the plus 0 on there. We'd probably just write it just like that. Okay, last one, starting point. Okay, on this one we do have to go up. It starts at 3, so we're going to say 0, 3. The slope, the rate of change, gosh, it looks like this is -1 also. Okay, so that means the equation is y equals -x plus 3, and there we go. Now, this is writing the equation from a graph, and we're thinking of this in terms of starting point and rate of change. This could also be considered like a context. So we're given information, we're given a picture of the information, then we need to write down the equation. Okay? Now, in these next couple problems, these are going to be a bit more of a story problem to figure out. So it says, identify the starting point and the rate of change, fill out the table, create a graph, and write the equation. So if we've done this correctly, all of this stuff should match up. The points that we do on the table, the graph should match up with the table, and the equation should describe the graph. Okay, so it says a Salt Lake City taxi service charges an initial $2 flag drop fee, so they charge you $2 just to get in, and then $1.50 per half mile. Let X represent miles and Y represent the cost. Okay, so I'm going to go ahead and put that down here. This is like our X and this is like our Y. So this is going to be money over here. So this is going to be miles and this is going to be dollars over here. And then it says, then write an equation to figure out how much X miles will cost. Be careful, label and scale your axes appropriately. Okay, so we've labeled them. We're going to have to scale them in just a second. So the starting point. Okay, so if we go 0 miles, now assuming we hop in the taxi, stop and think about this. If you hop in the taxi, the flag drop fee is your the fee just for getting in the taxi and tell them where you need to go. The minute that happens, they push a button and it sets the meter and it automatically charges you that $2. You haven't even left the curb yet. You haven't even moved yet, and it costs you $2. So at 0 miles, it costs you $2. Then it costs $1.50 for every half mile. So let's put a half mile here. We'd have to pay the $2 flag drop fee, plus we went a half a mile, so that's going to be another $1.50. So that's going to be $3.50. Okay, make those look like dollars. Okay, after 1 mile, we're going to owe them another $1.50, so that's going to put us, let's see, $3.50 plus $1.50, that's going to be $5. And if you stop and think about this, if it's $2.50 per half mile, if we double this, this is going to be $3 per mile. Okay, so $3 a mile in this particular case. And notice we went from $2 to start off with our flag drop fee when we haven't moved at all, to $5. So then 1 mile, 1.5 miles, 2 miles, and 2.5 miles. So let's see what this is. That would add another $1.50, so that would be $6.50. Add another $1.50 to that, so another 50 cents would be $7, and the dollar on top of that, that would be $8. Okay, so $8 here. And then $9.50 once we go another half a mile. Okay, so let's think about this. Let's scale this. We've got plenty of room here, so let's scale this in half miles. So let's go 0, 0.51, 1.5, 2, 2.5. So 2 and 2.5. Okay, we could scale it differently, but let's just go with that. And then let's scale this in. We've got 50 cents here, so let's do this. Let's do this as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's our money right there. So when we start off, it costs $2 just to get in. Okay, there's our flag drop fee. After a half a mile, it's going to be $3.50, so that's going to be right here. $3.50 after half a mile. After 1 mile, it's going to be $5, so $5 is right here. Now, this makes me feel a little bit better. We've scaled the axis and we're starting to graph these data points, and notice that it makes a nice straight line. Okay, so the next one, $1.50. Let's see if this lines up. $6.50 between 6 and 7 would be right there. $2, or it's 2 miles would be $8. That looks pretty good. See how everything's lining up. And then at 2.5 miles, $9.50. So there's 9 and there's $9.50. So we get this. Okay. And again, if we make our points nice and fat, everybody can look at that and say, hey, I know exactly where this person was going with these points. Okay, now let's write the equation. Now, if we were just told, hey, write an equation that represents this situation with this taxi and everything, that might be kind of hard. You might be good at it, but a lot of people struggle with this. So here's the cool thing. Once we've got a graph, we can ignore everything else. We can ignore the table, we can ignore the original problem, and we can say, hey, wait a minute. I know where this starts. It starts at 0, 2. And I know the rate of change. The rate of change is, and let's do this. Let's go from one nice point to the other nice point. It goes like that. Okay, that is up $3 in 1 mile. Or if I did this one, that's up, I'll do the next one up so we can see it. That's up from 6.50 to 8. That's up $1.50 in a half a mile. So if I did 1.5 divided by 0.5, that would end up being 3 over 1. And if I did 3 over 1, those are the same thing. Okay, so our rate of change is 3 over 1. But remember, the vertical represents dollars, and the horizontal represents miles. So this is $3 per mile. $3 per 1 mile. And lo and behold, that kind of matches up with what we came up with before. So let's write down an equation. Whoops, we got the rate of change is 3. Okay, and we'll write $3 per mile. Okay, so the equation would be, we need the slope. The slope is the rate. So that's going to be 3. We'll put an x right here, plus the y-intercept. That's our starting point. That's where it crossed the y-axis, so that's going to be a 2. So we're going to circle that, but remember, we've got to tell people what x and y represent. So in this particular case, let's look down here at the x-axis. That represents miles, and they said that up here. We also transferred that down here. And y represents cost. Y represents dollar cost. Okay? All right. So that's how we take the context of a problem and we write down a linear equation for it. And we'll get quicker as things go on here. So let's take a look at this next one. It says you're going on a road trip with your family. You've already gone 30 miles when you decide to write an equation so you can predict when you will arrive at your destination. The speed limit is 75 miles per hour on the freeway. If x represents hours and y represents miles, write an equation to figure out how many miles you will have traveled after x miles. After x hours. Use an equation to find how many miles you will have traveled after 6 hours. Ooh, a bunch of information here. And it does say find the starting point, rate of change, create a graph, write an equation, and answer the question. Okay, initial point. The initial point is going to be when we kind of start our stopwatch here. How many miles will we have gone already? So you've already gone 30 miles when you decide to start predicting how far you're going to drive and stuff like that. So our starting point is 30 miles. Our rate of change is going to be our slope. There is a rate right there, 75 miles per hour. So this is going to be 75. So could you write an equation for that? If you could, that's awesome. If you can't, let's stop and think about what's going on here. We're measuring hours, so we're going to use x right here, and this is going to be, this is going to be miles. And if you have any trouble with that, let's write down 75 miles per hour. There's our unit rate, okay? So what that means here is we've got the y's on the top and we've got the x's on the bottom. So that means miles would have to correspond with y's, and the bottom is hours, so that would have to correspond with x's. Okay, so we start off at 30. So let's do this. We're measuring this in hours, so let's go, let's measure this in like 15-minute increments. So let's do this. Every 4, that's going to be an hour, and that's going to be 2 hours, 3 hours, 4 hours, okay? And let's measure these in, let's say we measure these in 5s, at least 5s. So this would be 5 miles, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, okay? So we start off at 30, so we're going to put a point right there, 0, 30, and then 1 hour we go 75 miles. So there's our rate, 75 over 1. So we're going to go up 75. So up 75, gosh, that would put us up here at 105, and then over 1 hour. So it's going to look like this, okay? All right. So our equation would be y equals our slope, or our rate, 75x, plus our starting point, which is 30 miles. So there we go right there. Now, 6 hours is way off our chart right here. It would be way off the graph, way off the top of the screen. But we can find this because we know what each one of these equal, or we should, and this is where it becomes really useful to write down what each one of the variables represents. So on this one, let's go ahead and write down x equals hours and y represents miles. So if somebody said, how many miles after 6 hours, what they're saying here is x is equal to 6. So we're going to take that and we're going to plug it in right here. So we're going to get y equals 75 times 6 plus 30. 75 times 6. I'm going to grab the calculator here and plug that in. So I've grabbed the calculator, I've plugged in 75 times 6 plus 30. I ended up with 480 miles. 480 miles. So the answer on this one is 480 miles. Now, you may be pretty clever and be able to figure out the answer to that without writing an equation, but if you did, I guarantee if you think back through how you figured it out, it comes back to something involving 75 times that 6 plus 30. It involves that starting value of 30 and then that rate of change of 75. Okay, let's take a look at one more. It says same thing, identify the starting point, the rate of change, write an equation, and answer the question. So there's no graph required here, but we do want to figure out what the equation is. So here's the situation, here's the context. Courtney has a coin collection. She already has 48 coins in her collection. Now if you stop and think about that right there, that's what she's starting with. So let's say that's her starting value. Okay, her starting value is 48 coins. She plans to give away 3 coins every single week. So every single week she's going to give away 3 coins. Think about what that is, 3 coins per week. We'll come back to that in just a second. If x represents weeks and y represents coins, so let's go ahead and write that down. X equals weeks, y represents coins. Write an equation to figure out how many coins she will have after x weeks, and then use the equation to find out how many coins she'll have after 13 weeks. Okay, so let's come back here. We know that x is going to be weeks and y is going to be coins when we write down our equation. Here's our initial point right here, and this is our rate of change. Our rate of change is 3 coins each week, and she's giving it away. So if she's giving it away, the number of coins is not going to go up, the number of coins is going to go down. So we would have to have a negative rate of change. Whoops. So that's going to be -3. And if we were to write that, that would be -3 coins per week. So let's write down the equation. It would be y equals, remember the rate of change is going to be -3, times the number of weeks plus 48, and that right there is our equation. So we've got the initial point, or the starting point, the rate of change is -3, and then we've got our equation. Now, it says how many coins does she have after 6 weeks? Remember, x represents the number of weeks, so this is just like saying x equals 6 like we did on the last one. So we're going to plug that in there. Oh, I got a problem here. The original problem says that it's 13 weeks. So let's change that to 13. I'll get that changed in the notes. So after 13 weeks. So we're going to take this and we're going to plug it in right there. Okay? So we get y equals -3 times -13 plus 48. So this is going to be y equals, or sorry, not -13, +13. So -39 plus 48. 13 times 3 is 39, yep, and negative, because negative times a positive. So this is going to be y equals, she's going to have 9 left. 9 coins left after 13 weeks. Okay? All right. That is how we write linear equations and use linear equations in context. I do want to show you one more thing. How many weeks would it be before she has none? So how many weeks would it be before she has none? So this is just kind of an extra problem here. When does she have 0 coins? When is she out? Well, if we're talking about coins, that means y equals 0. So that means I could put a 0 right there. So 0 equals -3x plus 48. And let's solve this. Subtract 48. So this is a -48 equals -3x. divide by the -3. Those are going to cancel. And negative divided by negative is positive. That's good because we're talking about the number of weeks, and 3 goes in there 16 times. So 16 weeks, and they are all gone. Okay? All right, extra little bit right there. These can be challenging. A lot of people struggle with story problems and figuring out how to use math in context in the real world, but it is a very valuable skill, well worth putting in the effort.